Welcome to the second half of our tutorial. We'll begin this second half by describing our approach for explanation of property violations in control flow temporal logic. Our ultimate goal in explanation is to point out to software engineers the differences in characteristics between dynamic runs that violated a specification and those that satisfied it. Our work specifically focuses on extracting information about how program paths vary. This is possible because of the low-level nature of control flow temporal logic. For example, in the case of the formula on the left, we have the time between operator, and this places a constraint of the time taken to reach the call of the function calculate something from the change of the variable a. Specifically, if the control flow between these 2 points in the source code were to have different possible paths, then we would be interested in whether certain paths would be responsible for a higher time between the 2 points. Now, before discussing our theoretical contributions in depth, we highlight that theory is only part of a successful explanation approach. The results of any approach must be made available to software engineers in an actionable format. So in this section we present both our theoretical contributions and the layer that makes them useful to software engineers. As I mentioned previously, because of the low-level nature of control flow temporal logic, we will focus on explanation by analysis of program paths. In particular, we will introduce an approach for comparing paths taken by multiple runs of the same function, since control flow temporal logic formulas are written over individual functions in a system. We don't yet consider explanation using interprocedural paths, but we highlight that analyses like this are possible using the offline analysis tools provided by the VyPR ecosystem. Now, the ultimate aim of using program path analysis for explanation is to derive a set of points in a function's code at which a set of paths disagree, and then combine the subpaths taken at those points with information on specification's satisfaction or violation. To illustrate our work here, we will be using our case study at CERN as an example. Here we see a code listing that is representative of our case study at CERN. In particular, we have a condition with another conditional nested inside the first clause, and then we have a try except block afterwards. We will be interested in measuring the time taken to move between the initial assignment of P at the beginning of the code and the final call of the database commit function inside the try except block. Now, we know that paths will differ at the first branching statement, but recording the predicate P may not be space efficient. Further, the control flow in either clause may also be non-trivial, so recording only P may not suffice. Ultimately, we can conclude that we need a more general approach for recording and comparing program paths. Our approach to recording and reconstructing program paths consists of a 3-stage process. First of all, we insert instrumentation code at branching statements in code, identified using the symbolic control flow graph. Second, we use the instrumentation code to build up a program path, and the third step is done offline. In particular, we reconstruct program paths as paths through symbolic control flow graphs, using sequences of conditions built up by instrumentation. Here we see the same code listing as before, from our case study at CERN, along with 2 instances of its symbolic control flow graph, each one showing a possible path through it. This sets up our consideration of the path comparison problem. In particular, in this case, we see that we have 2 paths, each diverging at the same point, namely the first conditional in the code. We would like to be able to detect this divergence automatically given an arbitrary set of paths. Our approach is to use context-free grammars. Now, the first question to ask here is, how do we transform a symbolic control flow graph into a context-free grammar such that any path through the symbolic control flow graph can be represented with respect to that context-free grammar? Now, a possible solution here would be to see that a symbolic control flow graph could be converted into an automaton, and then from here we can use an established algorithm to convert the automaton into a context-free grammar. However, this makes seeing divergence and later convergence quite difficult, so we propose an alternative approach. In particular, we remove the automaton stage altogether, and instead we convert symbolic control flow graphs directly into context-free grammars, but which acknowledge the special structure of symbolic control flow graphs. Our technique allows detection of disagreement and, significantly, later agreement. The translation from a symbolic control flow graph into a context-free grammar involves mapping non-terminal symbols to symbolic states and terminal symbols to edges. This carries the intuition that a path through a symbolic control flow graph is a sequence of edges. Therefore, any context-free grammar should generate a sequence of edges. And here we have an example segment of a context-free grammar. In particular, we have the vertex, which signals a call of the function self.processIOVs, and from this we can generate an outgoing edge, and then the next vertex along, which signals both a change of the variable new tag and a call of the function func. Now, as usual, this rule would be recursed upon, so the vertex with new tag and func would be used to generate another outgoing edge, and this would carry on to generate the entire path. And now we see the first example of our scheme's acknowledgement of the special structure of symbolic control flow graphs. In this case, we show the rules that are used to generate paths through conditionals that are identified. The first step in this recognition is by identifying that a vertex, in this case P and predicate 1 at the top of the symbolic control flow graph, leads into a vertex that is the beginning of a conditional block. We can see that the difference here is that because we've detected that this vertex leads into a conditional block, the rule is written differently in the context-free grammar. First of all, we get the normal outgoing edge, and then the subsequent vertex, in this case conditional, but then we also include the post-conditional vertex. We do this because the resulting structure of parse trees with respect to this context-free grammar allows us to do certain operations that ultimately detect divergence in paths. By applying our full scheme from the inside of a symbolic control flow graph towards the outside, we get a context-free grammar like the one shown here. We see that non-terminal symbols on the left, highlighted in red, are vertices, or symbolic states from the symbolic control flow graph, and on the right we have terminal symbols as edges, and then further non-terminal symbols that can be recursed upon to ultimately generate paths. In the first example highlighted here, we see a normal vertex with no special structure, so the right-hand side of that rule in the context-free grammar is just an edge and then a subsequent vertex. We also see that the vertex at the beginning of the conditional block allows one to generate paths through either clause of the conditional. Now, important to notice is that the vertices at the end of a conditional block also have special structure. In this case, we see that one of the vertices at the end of the block only maps to an edge and not to the subsequent vertex. This is because the subsequent vertex is a post-conditional vertex, and this is included in one of the rules that we saw earlier. Again, this special structure of the context-free grammar allows us to generate parse trees that make the detection of divergence in paths straightforward. We will now see two examples of parse trees derived for paths with respect to the context-free grammar derived from this symbolic control flow graph. So here is the first, and here is the second, and it's already clear that these two paths generate quite different parse trees. Now, our approach for detecting disagreement in paths revolves around intersection of parse trees, which yields leaf nodes with vertices. Since vertices are symbolic states, which are non-terminal symbols, we know that parse trees like this are representative of the disagreement between multiple paths. In particular, to represent this fact, we refer to these significant vertices as path parameters. This naming convention carries the intuition that vertices can be given values, in particular subpaths, for a region in which multiple paths disagree in code. Now, to reiterate on our previous point, theory is only as useful as its interface with its users. If a tool is badly designed or requires too much familiarity with the underlying theory, the utility of the underlying theory does not really matter. This is the problem that we address next. To provide an interface between our underlying theory and the software engineers who will use it, we've developed an ecosystem of tools for instrumentation, monitoring, and explanation. For example, we have the VyPR core, which is highlighted in red, and this consists of the specification library, the instrumentation process, and the online monitoring. We also have the server, which consists of an insertion API, an analysis API, and a relational database to store all of the data obtained during monitoring. And finally, in blue, we have the analysis tools. And these consist of a web tool, which we'll demonstrate later, and a Python library, which we'll also demonstrate later. We provide a web-based analysis environment as an analysis entry point. The idea with this tool is that very little knowledge is required of the underlying theory. Instead, software engineers can explore the data obtained during monitoring using an intuitive and powerful web interface. For cases where more complex analyses are needed that can't yet be performed with the web tool, we provide a Python library. And while this requires more knowledge of the underlying theory, it allows significantly more flexibility. Our web-based analysis environment is a web application that wraps around a dataset generated by VyPR's instrumentation and monitoring processes in order to provide engineers with a visual interface for exploration of verdicts. The general pattern of use is exploration of verdicts in order to observe incorrect behavior and then ultimately to explain it. The architecture of the web tool is as follows. We start with a dataset obtained by instrumentation and monitoring, and then the web interface's backend performs some post-processing to get certain explanation data ready for the engineer to use. The web interface then allows verdict listing, measurement plotting, and path comparison and highlighting. Ultimately, all of these features are exposed to the software engineer through an intuitive interface, so quite complex and sophisticated analyses can be performed using just a few clicks in the web browser. We'll now give a live demonstration of the web tool being used to analyze the performance of a service used at the CMS experiment at CERN. So this is the first screen that you see when you open the VyPR analysis environment. So we see that on the left we have the list of specifications written across our service. So this is the service that we've applied VyPR to in our CERN case study. And on the right here you see an area where we will soon see a specification being listed as well as a code listing. So for this initial example, I'm going to select this specification that's written over the check hashes function. And this is a specification that places a constraint over the amount of time taken by a function called find new hashes. So I'll select that. The next thing that happens is I get a list of function calls. So I can scroll through and select these individually. However, given that in this case there are 4,000 function calls, we have the option to select all the function calls within an interval. So another thing about this display is that first of all you get the timestamp of when the function call started, you have the duration in seconds, and then you have the result of all of the specifications over that function with respect to the one that we selected. So we go back here, we wait for it to load again because 4,000 calls, and so we see here the first one. This means that there was a verdict during this particular function call that was false. This green indicator means that there were no verdicts that generated false, all of them generated true. So now I'm going to select all of the function calls between 1254 and 1330. So now I click filter calls, and you see that all of the function calls, all of the relevant function calls have automatically been selected. Now the key next thing to see is that the specification has been left alone, but in the code listing we have this highlighting of relevant lines. So the first line that's been highlighted is the line hashes equals and then all of this stuff on line 251, and this is the line that's relevant to the quantifier in our specification. So to reflect this, we show that first of all it's a binding, so binding an index 0, and we make this clickable. So when I click here, the next thing for me to do is to select part of the specification which, under the binding that I've selected, I want to see measurements from. So if I now select this q.next call of find new hashes, then this will start from this line and show me where instrumentation identified other points that satisfy this predicate of something being a call of find new hashes. So I click here, and you see that now I get some options over this line, which is a call of find new hashes. So I click here, and well, I get three options now. The first one is that I can plot the severity of observations from this point, and this essentially means that we will take all of the measurements with respect to this specification, and we will plot some metric of how close those measurements were to satisfying this specification. So if they succeeded, then we will display them in a certain way, and if not, then we'll display them in another way. So I'm just going to open this plot now, and if I drag this into view, you see that a notion of severity is reflected by this negativeness of the values. So we know that if we drag the window down, we're measuring a time duration. So obviously this won't be negative, these measurements will not be negative. And so here we see that we have negative values because the notion of severity reflects whether or not something went well or badly. So in this case we have some violations. So if I filter out all the successes and I just want violations, then I see that, well, there's one here that has a severity of -10, and this just means that it was outside the interval defined by the specification by 10 seconds. And it's same here. If I have -207, then this was quite a bad violation. It means that the measurement was outside the interval by 207 seconds. So you can see that's quite a major failure. So now if I turn successes back on, you can see that these are all relatively small, and this is a characteristic that we often see in severity, which is that the violations, the bad violations, are often much worse than the good successes. And this is because, well, this is a natural characteristic of the fact that the only region inside which measurements can be good here is quite small, and the region in which measurements can be bad is, well, mathematically infinite, but practically it's much, much larger than the interval in which good things can happen. So of course, all the things that are bad will be in a much larger interval and they will be drowned out a little bit. So if I now just list the successes, you see that the best severity that we observe is 0.11. So much smaller, much lower order of magnitude than the violations. So now I'll close this plot, and now we'll look at the observations. So the observations are all positive, and these are just measurements. These are in seconds. So here I have the 207 second one, but we'll see that, for example, if I go back to the severity, then we'll see that the highest severity will just be 0.3 away from the highest observation. So if I again open severity, then we see a difference of 0.3. And this is, not surprisingly, the upper bound of the interval in which good measurements are classified. So if I now open the plot of observations again, we see that there are many very small times taken and only a few quite large amounts of time taken. But in this plot, there's no information about how things went with respect to the specification. These are just measurements that were taken in order to decide whether or not the specification was in fact true. Now, another thing that the analysis environment allows is that we can, for example, plot, or we can highlight the paths taken or up to a given measurement. So in this case, I have this line here, and it's quite clear that the program had to take some path through its code to reach this point. So in this case, there's only one path, and so we're about to see pretty much an error because no path comparison can happen. So if I click highlight paths by average verdict severity, then first I get this notice at the top that all the runs took the same time, analysis by path is unavailable. But you can see that now we highlight all of the instructions that were executed on the way to this instruction. And while in this case that's not very useful, we'll see in another specification example that this is an incredibly useful thing to be able to do. So now we'll look at another specification which is a more complex one with multiple quantifiers and multiple types and a different type of atom, sorry. So here you see we have, first of all, we have a one for all, and then we have a second for all, and this is essentially just tracking all of the things that happened in the future of this quantifier up here. And then inside the specification, we have this mixed atom. So first of all, we care about the time taken to get from this state Q to this state, which is at the end of the next call to this other function. And then once that happens, we care about whether it's in this interval 0 to 0.1. And I can already tell you that this constraint is very tight, so we'll see a lot of violations. And as you see, we see a lot of red going down here. So this was an early version of the dataset before we realized that this constraint was too tight and that we had to loosen the constraint in order to actually see how the system was really behaving. And this is an important part of writing specifications, actually tuning them, because at the beginning you might write a constraint that's way too loose, and so you don't find any actual information about your system. And you might also write a constraint that's way too tight, in which case apparently your system is always behaving badly, but in fact the specification doesn't describe well the expected performance of your system. So again, we're going to show this time, and I'll filter this. So an important thing when we do this, when we select function calls, is that the bindings that are displayed in the code listing on the right are reflective of what is executed across all of these function calls. So if I were to deselect all of these and then just select one, which only traverse one path, then a couple of these bindings or one of these bindings might disappear. So in this case, we've selected quite a few function calls, so across all those different function calls, all of the paths have been traversed through this function, so we list all the bindings. So the most interesting case here is if I select binding 1. And this is, so you see we have color coding, we have turquoise matching this statement because, well, this was a change of the variable self.destination tag name. And here we have a call of session.commit, which is in the future of this change here. So, well, first of all, this is where we have two bindings, because if we click here, then we have two future calls of session.commit. So this will generate two bindings during instrumentation. And then second of all, once we click on one of these bindings, we see that now we have a slightly different selection process that we have to go through in order to narrow down the points in the code that we care about. So first of all, the selection here is slightly different to the previous example. And this is because in the previous example we had this binding, we had this quantifier, but then the specification was doing some kind of transformation on what the quantifier was giving it. For example, we had a change of a variable, and then we had the next function call along from that variable. In this case, we don't really do any of that. We just take Q, we take it as it is, we don't do any further traversal on the code, and we take C.result. So we're not doing any complex traversal on the code, we're pretty much taking what we get from the quantifiers. So at this stage I have two options. I can either select or fix one of these lines that is associated with the variable Q, or the one that's associated with C.result. So I'm going to go with Q, and I'll see that when I do this, I get an options button next to the appropriate line that is belonging to the variable Q, because Q is all changes of this variable. So if I click this, the one option that I get is that I can select this statement and highlight others that could form a pair. So an important thing to realize here is because we have a mixed atom, in order to do any kind of plotting of any data from it, we need 2 points to fix or to select to know which measurements came from those 2 points. If we only select one and we want to narrow down the measurements by which places in code they came from, then we have a problem, because we then have to select data from multiple points in code, and plotting it becomes a little bit nonsensical. So we have to select the 2 points that correspond to the two parts of this specification. So I'll now click this, and this will tell me that, okay, the next thing you need to look at is down here. So this means ultimately that I've selected binding 1. Binding 1 was these 2 points, line 42 and line 117. I then clicked Q, which mapped to this line, and then when I went to select the other line that formed the pair so that I could measure the time between them, the only other available option was this one, because we've already fixed the binding. So now here I'll click option, and we have a few different things that we can click. So first of all, I can select the statement and just plot observations, so I'm going to do that. And you see that, well, all of them, if we look at our specification, the upper bound is 0.1, and well, all of them are above 0.1. So these are observations of the time taken to reach this statement here from this statement here. So you can see that this is a really useful interface in that we can actively interact with the code and plot measurements taken from the parts of the code that we've selected. So that's quite a powerful ability to have when you're analysing your code. So I'm going to close that and now open a separate plot severity window. And you can see here, as expected, all of the severities are negative because every observation is a violation. If I just display successes, then I won't get anything. And also, as you can see, there's some quite severe violations down here, but most of them are actually quite close to the interval that we wanted. So it's also a useful thing to be able to do, to look at one of these plots and use it to be able to tighten your specification and say, well, it looks like more of the observations that we're getting in this case are possibly around 0.5, so if I maybe tighten my specification up here to 0.5, then the violations of my specification will reveal more insight, because they'll be the ones that actually do take a long time, rather than the rest of the observations here, which are quite clearly just the normal behavior of the program. So now that we've looked at these two, we can do the really interesting part of this analysis of this specification, which is we can take advantage of our path comparison machinery, which is implemented beneath all of this interface, and you can use this to detect the different paths taken and ultimately plot the times taken by the program when it traverses either of the paths. So I'm going to start this off by highlighting the path. So you see now that the code expands so that I can see all of the code, and the different paths that were taken are now highlighted. So first of all, I have highlighted in blue the instructions that were taken by every statement. So here you see I arrived here, and then I started from line 42 and I took these other statements here. But then I arrived at this conditional, and our path comparison approach has automatically detected that at this conditional there's divergence. And what we normally do is use the colour to highlight the average severity of verdicts across each of these paths, but in this case we have a lot of similarity. So what we'll do is click on this conditional, and we'll be given the option that we can either plot the observations with respect to the path taken or the verdict severity. So since all of the results in this case were violations because our specification was too tight, I'm going to just plot the observations, and you see that now we get this nice window where on the left we have a plot of the time taken, the measurement taken, and on the right we have the same code listing again. So we have the same code, as you can see, but we have this detected path difference where we can select which path that we want to analyze. So here we have the path starting on line 49, which is the first path through the conditional, but then we also have the path starting on line 88, which is the path down here in the second clause of the conditional. So if I select the other one, then my plot changes and I see different data. So I can really see how my code performed with respect to the path that was being taken. So this is a perfect way to be able to see whether the performance of your code depends on the path. And this is, as I've said in the previous slides, a step towards being able to really explain what your program is doing with respect to the observations that you measure.